Hello again. So in this video, we're going to look just briefly at the limits at infinity. So we used infinity in the last video, but this is something different. Let's motivate this a little. In many real world situations, your variable is time, and you want to know kind of generically what will happen in the future. So you're looking at an outbreak of a disease. So you've got a function, let's call it S of t. The input is the time since the outbreak started, let's say in days. The output is the number of sick people. And you want to know in the future how many people will get sick. And the reason this isn't an algebra problem is that we don't have a number that represents in the future. We're not asking what will happen in 1 day or 10 days or 100 days. We're just asking, by the time this disease has run its course, how many people will get sick? And the way we formulate a question like that mathematically is we'll say, okay, we're taking a limit, but time isn't going again to 1 day or 10 days or 100 days. To represent the future, we'll let time go all the way to infinity. So what we have here is a real limit. That is, in the material from the previous video, we have this infinity symbol, and I'm telling you, well, this isn't actually, the limit doesn't actually exist. That's not the case here. We're allowed to have the infinity symbol. This is a perfectly valid limit. In general, we're not going to be able to find these limits analytically in this class. So we have the concept, but actually finding them might be more difficult. There's a very standard tool that we often use to find such limits called L'Hopital's rule, but by convention, L'Hopital's rule doesn't get taught in applied calculus. calculus courses. It's very rarely in the textbook or the curriculum. We're going to look at then just one special case where we have a limit as we go to infinity, and we can find that limit. And that's rational functions. And depending on your algebra background, you may very well have seen this material before. Not the notation. The notation is presumably new to you. But let's create a rational function. R of x equals x squared plus x plus 1 over 2x squared minus x plus 1. And let's graphically investigate the limit as x goes to infinity of this function. So here's a graph of the function. The details largely don't matter, but we can see that as x gets big, y is hovering around 0.5. Like here, x is around 50, y is about 0.51. And if I go to the graph settings and I let x be really big, so when x is about 500, y is about 0.5. When x is about 900, y is about 0.5. It sure looks as if, as x is getting big, y is approaching 0.5. And again, I don't know your algebraic background, but when I say this number, 0.5, some of you are probably thinking horizontal asymptote. That's the horizontal asymptote. The degrees are the same, so we're dividing the leading terms to get the horizontal asymptote, and it's 1/2. And if you are thinking that, you are on the money. The limit as x approaches infinity is just a fancy way of asking for the horizontal asymptote. Now, maybe you weren't thinking that. Maybe you have never heard the phrase horizontal asymptote before in your life. If so, that's fine too. We can find horizontal asymptotes in a few ways, I guess I'd say. There's the thing I teach my college algebra students, and then there's the fancy calculus way. And I guess since this is a calculus class, I'll start with the fancy calculus way. To find the limit as x goes to infinity of a rational function, you divide the top and the bottom by the highest, pretend I spelled that right, by the highest power that appears. And this is one of these things that's probably a little cryptic until you see an example. Let's keep with the example we just looked at. The limit as x approaches infinity. That I'm going to give myself some room to work with here. X squared plus x plus 1 divided by 2x squared minus x plus 1. So of the powers that appear, we've got a second power, a first power, a second power, a first power. So the highest power that appears is an x square power. And now we do some algebra. A fraction with addition in the top and just a term down below. This breaks up. So the numerator of this big fraction becomes x squared over x squared plus x over x squared plus 1 over x squared. Down here, we have 2x squared minus x plus 1 over x squared. 2x squared over x squared minus x over x squared plus 1 over x squared. So now a bunch of stuff cancels. X squared over x squared becomes 1. 2x squared over x squared down below becomes 2. Then up top, we have 1 over x. X over x squared is 1 over x. No cancellation in the third term. It remains 1 over x squared. Down below, x over x squared, we get minus 1 over x. And then again, no cancellation in the third term, 1 over x squared. And now we ask, well, what happens as x gets big? What happens as x goes to infinity? Well, 1 just stays 1. 2 just stays 2. Everything else goes to 0. Um, any number, it doesn't matter what number, divided by x raised to any positive power. It doesn't matter what positive power. As x goes to infinity, fractions that look like this always go to 0. I mean, look at 1 over x. What happens as x gets big? 1 over 100 is small. 1 over 1,000 is smaller. 1 over 10,000 is smaller. 1/1,000,000th is smaller still. 1/1,000,000th even smaller. As x gets big, the fraction gets small. And that's true of all 4 of these fractions. So as x goes to infinity, the top is going to 1 plus 0 plus 0. The bottom is going to 2 minus 0 plus 0. The whole thing is going to 1/2. And I call this the fancy calculus way. And this is not, it is good to know this because this method generalizes. I think you'll see this in the textbook and some of the exercises and some of the examples. This method keeps working if instead of, having integer powers, you have a square root or something like that. But in college algebra, this isn't what I teach, and it might get a little tedious to keep doing this over and over again. The limit as x goes to infinity of a rational function p of x over q of x depends on the degrees of these polynomials. We can break this into three cases. Case one, the degree of the top is bigger than the degree of the bottom. In this case, the limit as x goes to infinity does not exist. Let's just go over to Desmos real quick. And let's change this so that the degree of the top is bigger than the degree of the bottom. Currently, they're equal. Currently, they're both 2. But I'm going to turn this top polynomial to a third degree polynomial. So degree 3 over degree 2, the degree up in top is bigger. And as x goes to infinity, y is no longer approaching a horizontal line. As x goes to infinity, y goes to infinity. So the limit doesn't exist. Case 2 is the reverse of this. If the degree of the top is less than the degree of the bottom, the limit as x goes to infinity of the rational function equals 0. In this case, nothing else matters. Only the degrees matter. The degrees are totally controlling the limit. Go to Desmos. Let's turn this second degree polynomial in the bottom to a fifth degree polynomial. Going to just erase the second power and turn it into a fifth power. And you see this rational function fluctuates a bit. But then as x goes to infinity, very quickly, this rational function settles down to 0. The limit as x goes to infinity is 0. And nothing else matters in this case, just the degrees. So if I took this top polynomial and I put a 1,000 or a 10,000 in front of the x squared, and I put whatever this is, 100 billion, it looks like, in front of the x, and I changed this +1 to negative 19,000. Well, The top is still degree 3, the bottom is still degree 5. 5 is still bigger than 3. It's still going to 0 as x goes to infinity. And then case 3. Well, what does case 3 have to be? We've looked at the cases where the degrees are different. Case 3 is where the degrees are equal, and the limit as x goes to infinity of p of x over q of x is the quotient of the leading terms. Or I really should say the leading coefficients. So what do I mean by that? Well, let's take a look. Let's go to Desmos and let's make these degrees be the same. Let me just go to the denominator and change that 5 to a 3. So now we have a third degree polynomial over a third degree polynomial. And in this magnification, we cannot see much of anything, just sort of blue smear. But the leading coefficient is the number in front of the power that gives us the degree. So the degree of the top is 3. It comes from this x cubed power. And the number in front of the x cubed is 10,000. The degree of the bottom is 3. It comes from an x cubed term. And the number in front of the x cubed term is 2. So the leading coefficients are 10,000 and 2. And that means that the horizontal asymptote is 10,000 divided by 2. The leading coefficient of the top over the leading coefficient of the bottom. Let's change this magnification and let's see if that looks like it's true. So here is the function. It is I mean, there's sort of a smear here. This is coming from some kind of vertical asymptote. But as x gets big, we see that this very messy looking rational function is just coming slowly down. And we have a horizontal line at 5,000. And it certainly looks credible from the graph, as if this horizontal line is indeed going to be a horizontal asymptote. And if we increase x, this does indeed end up being the case. As x gets very, very big, f of x ends up at about 5,000. Here, when x is 613,000, f of x is 5,000.133. when x is around 5 million. Now the function is 5,000.002. As x gets bigger and bigger, this rational function approaches 5,000. So that's the trick for finding limits of rational functions. Certainly, it's something you should know. But what I'd really, more than anything else, like for you to take from this section is this conception of what limits at infinity mean. That in general, when you're taking a limit at infinity, it's because they're asking a question about time and you want to know what's happening in the future. There is one other big application of this that we'll see much later in the course when we get to integral calculus. But for now, I will bid you goodbye and I'll see you in future videos.